here now. But I'm happy that some people are still here. So it's very, very nice of you all. I will talk a bit of high-performance computing. High-performance computing is, when I was prepared to talk a couple of weeks or months ago, or maybe quite more proposal, I had something very different in mind. When I came here this week, I figured out that many talks already covered topics from high-performance computing. There was a talk about CUDA, iCUDA, a tutorial by Ian about high-performance computing yesterday, which was really nice, and a couple of other talks. And so I just, deleted most of my slides, and I led some slides into the set and added some examples of what other people are doing in the field of high-performance computing with Python. Yeah, so maybe this will be the main focus of the talk. You will recognize these kind of slides because I didn't change the style of these slides. So just took them from them, or they sent me these slides via email and I didn't change them. What I will cover is first a few words about high-performance computing itself and where Python comes into place, and I will mention the tools and libraries that we can use for high-performance computing with Python. And this is the section where I throw out most of my slides because I didn't present any details here. Then I'm going to say something about debugging and profiling and present some applications where Python is used in the high-performance computing. And the last point I will also mention where the high-performance computing community and the Python community meet each other. This is actually not at EuroPython, not at PyCon UK. This is some other conferences and other events. As I said already, we had already a couple of talks here at EuroPython. These are the talks which where I attended or where I have seen the slides. We covered a lot of the high-performance computing stuff. I guess some of you were at these talks already. A few words about me. I'm working for DLR. DLR is the German Aerospace Center. It's like the NASA in the US. It's a German space agency and a research lab for aerospace, space, and transportation technology, and energy research, and security research, like both civil security and military security. And we are also like a funding agency for the space domain in Germany. We are distributed across currently 15 sites in Germany, and also I'm also distributed. I'm working in Cologne, in Braunschweig, and in Berlin, Germany. So I've got 3 offices and traveling a lot, so a lot of train rides from slides. I'm leading a group for software development. This group of systems and component software is currently about 15 people. And what we are doing as a group is, like at DLR itself, we do research in space and aerospace, but we do software development a lot. About 1,000 of our employees are working on software development. Most of them are engineers and scientists who just have to program in some way to do their task. And it's actually the target audience for our Python efforts. Because most of these people don't really want to program anything, but they must do the other research topics. There are people that really want to design a satellite or design a plane or maybe reports about traffic or other stuff. And programming is just needed, but they don't want it. we are developing the first things like mission-critical software, influence software, web-based systems, data management, workflow management systems, and of course, actually the largest part is high-performance computing software and scientific computing software. In this field is all the simulation software that we are developing, fluid dynamic simulations, elasticity, flight mechanics, and all other kinds of simulation in space and aeronautics. HPC, performance computing itself is well, it has applications in many different fields. They traditionally fields like natural biology, astrophysics, particle physics have high demand on high performance computing. In the last years, disciplines like biology and genetics and chemistry came to high performance computing, like immunity and also fluid dynamics, finance, oil exploration, all these disciplines with the engineering section are all trained using high performance computing for design and for regulation, for mining data and all this stuff. What's HPC? What's an HPC system? Actually, today, the laptop is not an HPC system. So, the top of the HPC systems are systems with more than 500,000 cores and 8,000 teraflops peak performance. So, counted every year in the top 500 list of supercomputers. The used version was just released this week in Hamburg, Germany. The top 3 systems currently are one machine from Japan or from China, one from the US. This is how high-performance computing machines look like. The largest computer currently in the world is the K computer. It's Spark processors. It's located in Japan. The second version is the second plate is Tianpei system in China. This is interesting because it's the largest computer with GPU, graphic processors. And the third one is interesting because it looks very nice. It's a system with Oak Ridge National Laboratory. This like more or less standard for processors.
Andreas, so the first computer is Spark-based.
Yes, it's
Wow.
again now.
I think that the top end was using commodity Intel machines.
There's some use, like there are a lot of machines on the top 500, well down. Yeah. Applications where Python is used. This is like a list of applications which has in the last months or years for which are people doing stuff with Python in these fields. Computation fluid dynamics is very huge in like the aerospace industry, automobile industry, and engineering. Customer simulation. Currently in the research section, mostly in the US, maybe in Japan. And we have also other fields like biomolecular, artificial intelligence, language processing, data mining, various fields, including finance and other. Also belong to this topic. Scientific visualization, because if you're doing large simulations, it's useless if you cannot do anything with the data that comes out. The visualization itself is a huge HPC problem today. You can write programs which run on a couple of thousand CPUs, and on each node there are pilot on maybe or more gigabytes. Then there are a couple of thousand multiplied by 1 gigabyte. It's a huge mass of data, and you have to analyze it somehow. And One of the biggest problems is to transfer the data from the high-performance computing machine to other machines where you can analyze it. So what we are doing at EuroPython is do not transfer the data. We analyze the data on the high-performance machine. Let's see, like reduce or analyze data back on like smaller systems, like up to laptops, and then do some visualization of to special topics in this field, the Pythons they are very useful is system administration and education. In many companies and research centers, administrators who use Python a lot to analyze literacy machines. Also in many labs and universities, Python is used for education of students because it's very easy. Later show a small example. So I'm working in the field of scientists and engineers. Why we are using Python there? We use Python there a lot at EuroPython. Currently we have about 100 people developing this Python. I guess we are one of the largest Python developers, employers for Python developers in Germany at least. And it's spread out into almost all institutes now. So this is because it's very, as I said, scientists and engineers don't really want to program, and if they must do programming, then it must be as easy as possible. And I guess this audience, you all know, this is really, really easy with Python. And had some calls that I found in the internet in the last months or years. One. That's also very nice.
So C++ also. Well, C++ people will ask about C++.
Sure, yeah. But in many places C++ is already there, and we have to convince people for some CPU, and in some areas Python is new.
Yeah. There's no hard code.
Oh, really?
As far as I know.
And this especially very good code which are used at TLR internally for communicating other like engineers. And one of the best code that I can use to convince other engineers is like some piece of Python code that works very well. So, which tools and libraries for HPC and scientific computing with Python are there? This is very different. We have like general tools, like very general tools like NumPy and SciPy. We have visualization tools. A lot of Matplotlib is very commonly used. I guess here at Python was a tutorial or some tutorial would be Matplotlib used. And other tools are Wizard, Mayavi, Chaco, but this case actually implemented in some other C++ maybe, but it's Python library. And especially for high-performance computing or for parallel computing, there are like systems of various like PETC from the National Lab in the US, or PyNPI, PyPar, and PyPy, programming like libraries like PyCuda, or OpenCL. On top of that, there exist a lot of tools from different domains. Artificial intelligence, biology, molecular, atomic modeling, computer sciences, some of them are based on NumPy, others are not. But what is, I think that is really important in this in the field of putting high-performance computing and Python together is working technology. Because currently, most serious applications are not implemented in Python. They are using like C++ or C or Fortran, so Fortran is very widely used in this field, or MATLAB. And in many cases, people don't want to re-implement the code. That's already here because it's tested for many years. We have DLR, we have an integration fluid dynamics code that is developed for about almost 25 years now. And all routines are really tested and validated against standard test cases in the industry like Airbus or EADS. And the people won't change any of these routines to language like Python. But what we can do is like makes the use of these high-quality codes in Fortran seem more easy in the usage for the user. That can be done by wrapping Fortran routines and C routines within Python interface. And this can be done automatically with tools like the compiles, size, and spec, other. I think this is very important. Few words about NumPy. NumPy is also library that is very widely used. I've not counted the talks here at EuroPython, which mentioned NumPy or which used NumPy, but there are a lot of talks, and Answer was simplified here at EuroPython. I also found out that the people that I'm dealing with in my daily work are also using NumPy a lot. So a lot of people that either ask me when can I get a training for NumPy now, because I have to start tomorrow with some work, whatever. And just the reason is because it's still very nice. It works very well. It's supported by Answer, and you can go like get support and all this stuff. I'm not going through the details of NumPy. That's not the topic of my topic. But the basic concept I like the NumPy arrays. On top of that, or another Answer is like SciPy. What's for proof of Python. This is really if you don't want to do anything from the ground up really new. You can use tools for different fields like signal processing, Fourier transformation, optimization, and so on. This is also a very important tool set because it saves you a lot of time if you want to do some tasks. The competitor in this field is really MATLAB. Extension modules. I don't know how many extension modules MATLAB has. They're really massive extension. Any kind of engineering fields or other fields, including like structured visualization, graphical user interface. But some people complain about the language, MATLAB language. If you want to change this to another like syntax of Python, you have to provide like good tools to provide similar functionality. SciPy is very good at that. We don't want to use NumPy or SciPy to program by hand. I think we have different chances, like different technologies, like threading, subprocess, or we use API programming, and we use libraries for GPU. One of the things that is widely used is parallel programming is MPI, Massive Parser Interface, and generally this is MPI that is the standard, the specification is the standard, but the implementation, let me say there are different implementations, whether there's implementation for machines or software implementation that you can compile a lot of machines. like MPitch from our national lab, and MPI for Python is like a wrapper around this native MPI. It works, for example, also with NumPy data types. It provides features of the MPI2 specification. So then it came. To use MPI for Python is more or less the same as writing MPI for the application is the MPI1 program, which distributes the processes to the performance machine. And the MPI library behind takes care of all the communication work. Writing of data and gathering data back to the node. And if you have limitations in your MPI implementation on your machine, but these limitations are also present at the MPI side. That's not extend the MPI implementation. How does this look like? Like a simple example is calculating P. Calculating P with a statistical method. Going like dots on the quarter of the circle. Sorry? No. Dots on the quarter of the circle, and then count the number of dots which are inside the circle, and you can multiply this by 4 and then approximation for P. If you want to do this in parallel, it's really easy, just some importing modules that you need, a little bit set up the API, and get the rank, the node number of your node, and start this program, and then spread out like a couple of samples on the different nodes, and afterwards, if you are you make no node, the head node, afterwards you can print the result. Programming for GPGPUs, general purpose computing for graphic processing units. It's a little bit different. GPGPUs, the architecture is you have many cores on each node. Each core is very simple. And this is why we go for like stream processing with data which is independent. You do not have much communication between each computing node, each core. But if you have applications that have many parallel tasks, parallel GPUs are very good. They are actually probably for graphic cards is mostly today done with two technologies, like with CUDA from NVIDIA or OpenCL, which is the standard for GPUs and other processors. CUDA is a platform for C programming on GPUs. Python by the CUDA, and OpenCL is like a framework for many platforms, including regular CPUs. There's also the Python binding PyOpenCL. PyCUDA and OpenCL are both like the same quality for the village. They integrate with NumPy, and things like error handling is done very well, like errors on the C side or the lower level side are translated to the Python section, for example. So it's very convenient to use. Computing model, or skip this. The computation example in PyOpenCL, just to show how short it is. The number of lines is even shorter than in the API work. Just do a couple of samples, distribute the samples, and visit the course, and afterwards you get the results from the different course plan and like before they get
What's the RNG?
Sorry?
It looks like there's a RNG as part of OPCL. Which RNG is it?
Random number generator.
It looks like, yeah, it looks like it's part of the standard OPCL definition. So which one is it? Is it bit more simulations?
Oh, I don't know. Special implementation for CUDA, which is very interesting, is copy. CUDA, PyCUDA, etc. PyCUDA, etc. is a reflection of the CUDA-C language, but NVIDIA developed their own Python data for GPU. Like these are slides which I get from Michael Dart from NVIDIA Research. First slide, you can see again the general architecture of the GPU. The second slide here is the small example you can see. One problem which is run on the host, one problem that is distributed to the different cores of the GPU. Possibly like any C code. This is like on the host, the code on the right side is distributed to the different GPUs. This works very well if you want to program in C, but it's very hard. So a student at our labs that was asked this CUDA program in C, they didn't have fun. One of the most important things that our lab is having fun at work. It works with languages like Python or C. And I guess NVIDIA figured out the same. Talking to their customers. So the summary from them is not everybody wants to know the environment. Especially in our target group, like engineers and scientists, they couldn't find any serious scientists who want to load their program or see on GPU. To that is people, they implemented an Python interpreter for GPUs. You can do like this is an example for like a vector multiplication in just very small Python code. And if you know Python, it's very easy to understand. So, CUDA program in Python is really easy. And EuroPython is really nice. Actually, customers of NVIDIA like it or we like it. I don't know if it's already generally available. But it's only a subset of the Python on the program of interpreting for GPU users on the big improvement.
So I know that PyCUDA is a couple of years old now, it's fairly mature, and PyCL is similarly mature. How new is Copperhead? How much would you regard it as mature?
No. Also my last information was that it's not mature, so I'm even not sure if it's a product already that you can get. If it's a product already that you can get from them, like any other product. But they started, I guess, 3 years ago, or 4 years ago. That's still not yet. Another topic in high performance computing is always debugging and profiling. As I said, in HPC codes, in many cases, we have a combination of C and of Fortran and Python. they do programming like very obviously is Python debuggers from the Python side, and you have special debuggers for C on the C side. For example, like the debugger that very widely used is commercial debugger, special extensions like for parallel programs. And also profiling is very important guide for computer field. If you are looking and searching for the best performance, you have to really analyze where are the performance losses in the code, where are bottlenecks. Because Python sites there are also codes, profiles which work very well. A special system which I will show now is the type code performance system from the University of Oregon. It's like a performance analyzing system for all kinds of languages. Python, C, Fortran, Java, and it works with Tutor, API, these types, all the technologies from the platform. As you can see here, I'm not going into details. It has a complex architecture, which basically does instrumentation for the code. So the effort for your code is, if it's done automatically, it's very low. It's very easy to use, like our system. It comes also with like a very nice visualization tool. And can analyze like the scalability of the columns, so different number of CPUs or nodes. And it's designed that this works very well with Python. So to instrument Python code, what you use power performance analysis. Python is just to start out at one with your Python main module, and then the output will show something about Python performance, which you how much time? 10 minutes? Some applications that people are using in the HPC field. One is from this is the what is it? One new Institute of Science and Technology in Korea, in the south. It's an actual equation solver. And it's, basically, actual equation is basically used for like all kinds of waves. Microwaves, radar, light programs, and so on. So, if you're interested, you can go into mathematical details here. I understood that when I was a student, but after the exam, I forgot everything. And they also, the opposite thing, they have routines implemented in Fortran or C. I think they already implemented in C. Integrate Python script around Python web for each module. They can steal the whole simulations in Python. So it's also possible in parallel or very large machine. South Korea is the country where they're not high performance computing, but they are working a lot in this kind of field, and they have a lot of resources for the HPC and buying machines and so on. It's a very good infrastructure. Another example is job simulation. It's a field where I was working for many years. This is the work that we are doing at EuroPython. It's called Flow Simulator. It's a framework for CFD simulation, like flow around this military airplane. And projection fluid dynamics mean you compute the flow around an airplane to design new airplanes or to evaluate existing airplanes or to optimize airplane designs. Classically, this is done with a simple process chain like this. solver, and like post-processing. As I said before, these solver and post-processing are have very high computational demands, and currently this simple chain will be extended with like a CT solver and the mesh adaptation and the geometry changes, the mesh, the mesh, and it will be even complexer if you have multidisciplinary computation simulations, where you not only simulate the flow about an airplane, but also simulate the structural mechanics, flight mechanics of the plane. This is the flight mechanics and structural mechanics. And what we did here is we built like ISO modules from each of these different blocks, flight mechanics and CT solver and so on. And Python modules might be maybe in Python program is like Fortran C, which is the main. And then something like that transport. And this is an explanation of the structure of the plane, which makes some notation. It's like a couple simulation of the flight mechanics and the structure. The architecture of this is the different routines. We have the data manager, which is besides what we have for the machine. We implemented this API, for example, and the access control. This is the data license which controls the whole application. And access control is actually implemented by Airbus. And the data management side is providing Python and another application, I can see this plasma simulation of which just a few words about Python and HPC communities. Their conferences, first two is they are obvious, like they have high names or high Python people around there. Like Sci-Fi is a Sci-Fi conference organized more or less by NSOL since 2008. It's Python for Scientific Computing Conference annually. And another conference here is this European Sci-Fi, Euro Sci-Fi, annual conference since 2 or 3 years. It will happen this year in August in Paris. These are conferences where many people are attending which are interested in Python. The third conference series, SC series, Supercomputing series, is a conference where almost all HPC people in the world attend. This is a conference even bigger than EuroPython, which is about 10,000 attendees every year. It's also annual every November in the US, and this is really the major event for high performance computing, which also is talks and this like exhibition floor. And at this conference, for example, most people are not going to talks on this stuff. It's like disturbing. They want to do business and talk about high performance computing and listen to talks and so on. But it's very interesting. You can get into very huge mass of people, and we had done a couple of years ago, like to go this Python with this conference and like convince people at like the HPC community conference. And what we did is like we do a tutorial and off sessions since 2009 at this conference. The tutorials is like called Python for Scientific Intelligent Computing, usually led by William Stalin from our national lab. In this tutorial, the people from the HPC domain can learn Python language. They learn things like NumPy, things for profiling, visualization of data, number of attendants is really growing every year. So it attracts more and more people. And another thing is the lots of professors sessions. It's like people who are loosely interested in technologies come together and talk about things like this small talks or discussions. And we had in 2009 the first professor session, and last year in the Philippines, and this year we will be session in Seattle. This is really a place where a lot of people which we don't know of that they are using Python come to the room and talk about Python. And it's also very crowded, so this is a large conference, but there are about 100 people interested, especially in Python, and doing interesting stuff in Python, as the example that I've shown in good. So I've no time, so my last slide. This is all these people have stolen the slides or get slides. Any questions? So to summarize again, is Python today is really useful HPC and good tools, but the most important technology today is like writing C and with Python.
I don't know if I remember well, but when I studied some current in C++, I learned that there are two different paradigms. MPI is one case, but there is also OpenMP. OpenMP is used when there are more processors that use the semi-shared memory. There is a worker or a library similar to OpenMP for Python.
Yes, there was one, but I think it's not maintained. Yeah, I know that there was one, the library was like actually, I think it was the same as the wrapper for the library, the wrapper for shared memory library. But I don't know what happened since the name of the last years, and none of it's still maintained. And also the number of shared memory machines are reduced very much. Times where we had these trade machines and so on. More people were doing shared memory or NEC wasn't really
Andreas, for somebody who wants to try MPI or CUDA and they've never tried MPI or CUDA, do you think it will be hours before they're starting to write code, or days or weeks? You give a guide to startup time.
For writing MPI and CUDA with Python?
So you haven't installed MPI, you've never written MPI, but you're an intermediate Python programmer, and you want to distribute your task to 100 machines, and the same for CUDA. Hours, days, weeks.
We found out that it takes hours or days. So we made tests like with engineers from other groups and gave them, for example, the copy that we get from NVIDIA, and it works very well. After the one guy was coming up with some like a very simple C solver in Copperhead and just Python after 2 days. But yet some stuff in Python already was just important.
Andreas, I'm just wondering, as far as I understood, you had to deal with a lot of HPC problems, and did you run into solving the HTC, the high computing problems, and if yes, did you make any use of Python in that case?
You mean like, let's see, simply talk on this stuff?
I mean, not trying to solve a problem as fast as possible, but rather solve a lot of small problems.
Okay, no, that's not, no, I have no experience of that. Like, our kind of engineering is not technology.
Other questions?
Have you considered to introduce Wi-Fi for a scientist to help speed up?
Yeah, we have yes, we considered this, and just the scientific student work for trying out Wi-Fi for like some to make performance analysis on small CPU solver Wi-Fi.
One part of pipeline is that it's hard to do extensions. You have C++ extension in the C++ lines of pipeline. It's more of an experimental things, but not many. If you have C code that's available through a C types, then you can do it. But the other ones, the Sway, the Cython, all these other wrappers that have been developed, have to basically redevelop the core pipeline. Yes.
Well, yeah, there's a light port of numpy. I believe there's a light port of numpy program. But that's, I don't know if that's the right way to solve the pipeline to numpy integration.
The pipeline we need is next, so we can now go over there and fill them. Hey, yeah, this.
I intended just to for Greek code, new code to be developed by scientists. Obviously, if you have C++ 3 or Fortran library which is already existing, you need a wrapper to use it in Python. You don't have to write it again in Python, just to use by Python. So I can come only for new libraries that you want to make with Python, for example.
Any other question? No? Oh. Is there any use of Cython and Shebskin inside the LR?
Yeah.
I guess for anyone who doesn't know, Cython lets you make C extensions, and Shebskin lets you compile code down to C code as well.
Which is Cython?
Much of Cython. I wonder if it's, do you use Cython and Shebskin internally?
Not in my department, but in other groups, yes. I have seen Cython, but not Shebskin.
Anyone else? Yeah, okay.